steady state equation, P equals PM. You start in P, you're in P forever. How many solutions are there? That was the kind of thing we were doing last time. Let's see what people said. Okay, really good split between exactly one solution and infinitely many solutions. One person said no solutions. There is at least one solution, so no solutions is wrong, but which of these two is it? 7 to 8 split is very close. Let's revote, talk to your neighbors, try to figure out, let's see if we can get to the bottom of this. I'll let you guys think about it a little bit, talk to your neighbors, and we'll revote and reconvene in, say, 2 minutes. So figure it out. Okay, it's open again, so you got to put in your answer. Even if you don't want to change your mind, you have to put in the same answer again. Oh, lots of people voting quickly. Okay, let me just do 1 minute. Yeah, I mean, half of you guys are wrong, right? So it's just like which half we don't know. Okay, let's do 1 minute here.
Would you say that we need P to be a value state? Because then if
Does half include the one person that said no solution?
Right. Well, that person's, I guess, is like the tiebreaker. Okay, it's not. Yeah. So like when I say half, you know, like within 70 to 30 is half. Like, you know, when you break a granola bar in half, that kind of half. Like not the math half. If I wanted to say math half, I would say 1 divided by 2 or something. Okay. Okay. Let's see how many people. Okay, 2 people haven't voted yet, but we're gonna stop in 10 seconds regardless. Okay, so how many solutions are there to the equation? After revoting, now people say there are... more people are in exactly one half. So before it was like a 50-50 split, and you guys discussed for a little bit, and some people who said infinitely many moved to exactly one, and that is wrong. There are infinitely many solutions. So you guys got less good after chatting. I'm not sure what happened. So maybe somebody can tell me why they chose exactly one, and maybe somebody else can tell me why there are infinitely many. Somebody who voted for... Let's go. Can someone who voted for this one be brave and tell me why they voted for that one? Yeah.
Well, there's the solution that we talked about last class, and I can't think of any other ones.
Right. So last class, I was on this whole thing. I was like, no matter what you start with, it always goes to 25-75. And I was like making this big deal out of like it doesn't matter where you start. You always get sucked into this 25-75 solution. That's the solution we care about. And then I did all this pen and paper math, and it came out with this 25-75. Like everything I did made it seem like there was a unique solution, right? Okay, so that's definitely true. All of that is true. It's the wrong answer. Okay, so why are there infinitely many solutions? Yeah.
I don't know. I just voted for both.
Okay, so if you voted for both, very clever. Does someone know why there's infinitely many? Yeah.
So long as the ratio of the inputs for the eigenvector remains the same, you can scale it.
Yes.
You'll still get the same answer.
Exactly right. So the problem is with this equation is that you can scale it. You can multiply by any scalar as long as it's in the ratio 1 to 3. So 25-75 was the example we were doing last time. That is a solution. But any multiple of that, so twice that works. 0.5 and I guess 1.5 also works. 1, 3, that works. -1, -3, that works. So this equation on its own is an important equation, but it doesn't have everything we need. And the reason last class I kept going on about this unique stuff, as long as you specify that it is an actual probability vector, that the sum of the probabilities is 1, then there is only one solution. So you got to be careful. Just the equation on its own, not unique, infinitely many solutions. In fact, there's a one-dimensional family of equations. But the ones we care about, there was only one solution in that problem, and that's because there's an extra equation that's missing, not on the board right now, which says that the sum of the p's should be 1. So why did I want to tell you this? Last time I did it all on pen and paper, and it all worked out. But the problem is if you just put this in the computer, you will get the wrong answer, because the computer, of course, will only do what you tell it to do, not what you want it to do. And if you tell it, please solve this equation, you're going to run into this infinitely many solutions thing. So let me show you that. This is the weather matrix situation from last time. So last time I got this solution. So the dots are by doing powers of the matrix, and the lines were from our theory, and that was this formula that I got last time. So 1 plus 3 over 5 to the n, 3 minus 3 over 5 to the n. And we got that from these eigenvalues and eigenvectors. And I did that sort of all with pencil and paper. I skipped the step where I actually solved them, and I just told you guys the solutions, 1, 3, and 1 minus 1. But then it all worked out, and you got this nice thing. Let's see, how could we ask the computer to do that, right? Because, of course, when it's a 2 by 2 system, you do it with pen and paper, it's fine. If it's a 100 by 100 matrix, you don't want to sit there and do it by hand. You want to get the computer to do it. So the first thing is to try to solve the equation. Okay, wait. This is eigenvectors and eigenvalues. This is kind of what I did last time. But let me show you this one first. So if you just try to solve p equals pm. Okay, I always forget. This projector cuts off a piece of the board. I don't know if it's very important, but let's rescue it. Okay. Okay. So if you try to solve p equals pm, how would you solve p equals pm? Well, NumPy has a solution called np.linealg.solve. And np.linealg.solve will solve equations of the form ax equals b. Let's get this somewhere. So if you do np.linealg.solve and you do ab, this will solve ax equals b. So this will tell you the answer x. So the solution to ax equals b. So we have the solution, the equation p equals pm. And so to make it look like an ax equals b, I move it all to the other side of the equation. You get p times I minus m equals 0. So p times itself is p times the identity matrix. So you end up with this identity matrix minus m equals 0. That almost looks like what we want. This is what we want, ax equals b. But the p is on the wrong side. So this is, again, one of the things you have to do is whenever you're working with computer algebra systems, they're always set up to work with column vectors. If you're working with row vectors, you got to tell the computer, please flip everything. And the way you can flip everything is by taking the transpose. So take the transpose. And if you do the transpose, you're going to get I minus m transpose times p transpose equals 0 transpose. And now it looks just like we got over there. So what you should do is you should do np.linealg.solve, and you should do I minus m transpose and 0. Okay, 0 transpose is still 0. Okay, let's put the 0 transpose so we know. So that should work. Let's see what happens when you put it in. And I might have forgotten the transpose over here. And it occurs to me when I did this. Did I remember the transpose? I forgot the transpose. Okay, let me put the transpose in. So it should be dot t. That should be what I want. Okay, and let me run it again. Okay, and I gotta go to, I need this button so I can go runtime and run all. Okay, will it get to here? Okay, so there we go. I ran it. I solved it. And I called this thing not helpful. And why is it not helpful? It found the solution 0, 0. So it says, here's the solution to this equation, p equals 0, 0. That is a valid solution to the equation you told me. And so that's quite annoying. So look, if you put in 0, then anything times 0 is the 0 vector. So there you go, 0. We want the non-zero solution. We want actually a solution that sums to 1. So this is no good. Okay, so what we got to do is we got to find a way to convince the computer to give us a helpful solution. How could you convince the computer to give us a helpful solution? And again, you should be thinking in terms of linear algebra. Once you kind of think of it, at least for me, in terms of pen and paper linear algebra, converting it into what the computer wants is sort of easier. So how can we, using the language of linear algebra, tell it, please give us a solution where the sum is 1? Let's think for a minute. Here, I'll put this back up. So far we have I minus m transpose of p transpose equals the 0 vector, or if you want, we could write it the other way. Yeah, let's write it the other way. I think it's easier to think about the other way, and then we'll do all the converting at the end. Let's do it like this: p times this thing equals the 0 vector. And that's not good enough. This equation is sort of underspecified exactly because the matrix M has a 1 eigenvalue, so I minus M has the 0 eigenvalue. That's the eigenspace we're looking at. We're looking for solutions in this eigenspace. There's infinitely many solutions, and we want to narrow it down to just one. So what could we do? What could we add to this page to narrow it down to the solution that we want? Yeah.
Does the magnitude of p have to be 1?
Yeah, that's a great guess. So this is a typical thing, is that you do something like this. The magnitude of p, which you write like this. The magnitude of p, normally people mean the Euclidean magnitude, right? So they'll say p1 squared plus p2 squared equals 1. Okay, actually this comes with a square root, but when it's equal to 1. And some programs have this kind of thing built in. So when you do minimizations and maximizations, sometimes it'll have this kind of magnitude thing built in. That is a great, fantastic guess, and that's almost what we want. I think we do want p1 and p2 sort of to be involved. We don't want the magnitude squared to be 1, though, because they're probabilities. So probability is squaring them. That's like some quantum stuff. We don't do that. So this is close, but not quite. So this is close. Okay. Anyone else have another guess? Yeah.
Does it have to do with determinants?
So when you go to solve this equation, sometimes you can do it with a determinant. So there is a determinant, sort of, you can think of it being baked into this equation. The one I'm doing is, it's not so complicated. So there's no determinant. Very simple. Very simple. It involves P1 and P2.
Is it Manhattan distance?
So the Manhattan distance is, so the people who are in my other class are very excited right now. This is what we've been doing. The Manhattan distance is the absolute value of P1 plus the absolute value of P2 equals 1. And that's almost what we want, right? That's closer than the squares, but you don't square probabilities. When you take the absolute value of a probability, if the probability is a probability, it's just itself, right? So this is the Manhattan distance, the 1 norm. And for probabilities, it really should just say P1 plus P2 equals 1. Equals 1. That's all we need to add. If we take this thing and we say, please also make sure that P1 plus P2 equals 1, then it should find the right solution. Of course, there is a chance it's going to find something like 1.5 plus negative 0.5 equals 1. But actually, we're guaranteed from that theory guy, the Frobenius-Perron theorem, that it's going to work out. So there will be an actual solution, and it makes physical sense that there is an exact solution. So this is the thing we got to do. We're going to have 2 equations, this equation and that equation. And we're going to put both into the computer at the same time. So if you just tell it, please solve equation 1, okay, we'll call this guy equation 1, then it'll explode. Or I guess it doesn't explode. It just tells you something not helpful. But you say, please solve equation 1 and equation 2 at the same time, and then it will give you a solution. Okay, but now the follow-up question is, how do you tell the computer solve equation 1 and equation 2 at the same time? You have to find a way to input that into the computer. And in general, if you have like a system of equations, it can be quite complicated to input it. But in this particular case, it happens that both equation 1 and equation 2 are completely linear equations. And any linear equation you can always write as some kind of ax equals b, where A is the matrix that stores all the left-hand side, and B is the vector that stores all the right-hand side. So we can just interpret this whole thing, which is really 2 equations, we can interpret it as one big equation with a big matrix A that sort of stores everything. And so what we're going to do is we're just going to stack. We're going to stack the matrix I minus M with the matrix that encodes P1 plus P2 equals 1. To do that, we're going to rewrite this one as P1 plus P2 equals 1. We're going to write this as P vector times 1, 1. So P vector times 1, 1 equals 1. And now it looks a lot like the other equation. We can do both of these together as one big matrix. So you can make a matrix like this. So equation 1 plus equation 2 together. What will it look like? It'll look like P times what? Well, you'll have I minus M, and then you'll have 1, 1. And I'm writing it like this. I'm saying take the matrix I minus M, and just next to it write the column vector 1, 1, and smoosh those together. Like we're gluing matrices together. Sometimes people call this gluing matrices. They call this an augmented matrix, which is, again, something they talk about in linear algebra class. And this thing is encoding both equation 1, which has the I minus M part, and equation 2 at the same time. Actually, it's only the left-hand side so far. I can put in the right-hand side. The right-hand side is going to be 0, 0. That's the 0 vector over here from equation 1 was 0, 0, and I'm going to put in a 1 over here. That's the equation over there. And if you think about it, it makes perfect sense. We have a 1 by 2 matrix times a 2 by 3 matrix. It has 3 columns, and that's equal to a 1 by 3 vector. So it's obeying the laws of matrix multiplication, and by making it 3 big, we have augmented it into a system like this. Okay, and you can see if you loved linear algebra class, then you can see what's happening is the original equation we had. This is, even though this is a 2 by 2 matrix, it's a rank deficient matrix. I minus m is only rank 1, even though it's a 2 by 2 matrix, and that is why there is a whole one-dimensional system of equations that solves equation 1 on its own. When you add equation 2, you've increased the rank by 1. So when you go to solve this thing, this 2 by 3 matrix is only rank 2, and you'll have a unique solution to this augmented matrix system. So by counting the dimensions and using what we know about linear algebra, you know this is going to have a solution. And this one you can enter into the computer because it's something ax equals b, right? It's the same as ax equals b, where now A is a 2 by 3 matrix and B is a 3 by 1 vector. Okay, so this is the one you're going to enter into the computer. Any questions or comments so far? Any linear algebra class questions? Okay, so let's enter into the computer. And earlier I said you can do np.linalg.solve. It turns out np.linalg.solve only works for square matrices. So you need to do something slightly different. There's another command, and that other command is this command. Okay, yeah, so this is kind of like a write-up of what I did. I said before we're adding this equation to it, and here are the equations. I minus m is our matrix. 1s is the vector 1, 1, and this aug is the augmented matrix of stacking together 1, 1 with I minus m. To do rectangular matrices, it's not np.linalg.solve, it's np.linalg.lustsq. LSTSQ. Does anyone have an idea what lustsq actually stands for? Yeah.
Least squares?
Least squares, yeah. So LSTSQ stands for least squares. And it works even if the matrix is a rectangular matrix. Here is the vector that we're going up to. Okay, when I did it on pen and paper, I said 0, 0, 1. Here it's 1, 0, 0. I stacked it on the other side. Hopefully that's okay. When you do the least squares thing in linear algebra, it'll find the best possible solution. So if there is no exact solution, it'll find you the closest solution. And there are some extra little tidbits you got to do. If you don't put rcond equals none, it will warn you that that means something. But don't worry about that. You have to find the 0 thing. The 0 is the solution. The 1 and the 2, it outputs some list with like how big is the error and things like that. But you just want that one. This is basically saying solve, if you can, for a rectangular matrix. And you'll see that it worked. So it outputs 25%, 75% for the thing. So that's one way you can do stuff in the computer. Okay. So I wanted to show you guys, to not leave you hanging on when you actually go to do the stuff on the computer, now you'll have this tool. And this is a very common thing, is like you'll have equations, that things you want to solve, and then you'll realize, oh wait, we also need to add in these other equations. We're going to see that in another setting, again with the I minus m matrix later today. Questions or comments about this stuff? Yeah?
Are these on course link?
Yes, so they were not yesterday, but now today they are. So there is a course GitHub now that has all these things, and I rewrote them a little bit and added some sections, so hopefully they're easier to look around at. Yeah, great question. Anyone else? Okay, there's one other thing that we did last time, is we did the eigenvectors and eigenvalues, and again I did that by hand, but here is the exact same thing on the computer. This one is, there are no tricks, you just need to know the command is np.linalg.eig, and so if you say, okay, let's scroll over this way. So if you say eigenvalues, comma, eigenvectors equals np.linalg.eig, then it will automatically compute the eigenvectors and eigenvalues. And then if you do that, you can compute powers if you want. Here are the eigenvalues and eigenvectors that I found. 0.21 is our 1/5 1. That's what we saw last time. These ones look a little funny. Minus 0.7 and minus 0.3 are the eigenvectors. Oh, right, they're stacked. again, because of the transpose thing, it's minus 0.7 and plus 0.7. That was the minus 1, 1 vector. And minus 0.3 and minus 0.9 is the 1, 3 vector, right? So it's not giving you the exact things we had before. It's giving you scalar multiples. It multiplied them by 0.7. I think it is making sure that they sum square to 1. So minus 0.07 looks suspiciously like 1 over square root of 2 to me. So minus 1 over square root of 2 and plus 1 over square root of 2. In any case, you can reconstruct the matrix M by using its eigenvectors, by using the kind of formula we had before. Eigenvectors inverse times the diagonal matrix times the eigenvectors. Okay. And you can also do the limit. So by taking powers, when you do powers of the diagonal matrix. And when you do powers of the eigenvalues, they are either 1 or 0. So the eigenvalues, because the eigenvalues are all less than 1 in absolute value, when you take them to really big powers, then the eigenvalues shrink down to 0 or they stay where they are. That's exactly what we saw with pen and paper math last time. We said that one of the eigenvalues was 0.2. That one just goes away. And the eigenvalue that is equal to 1, that one sticks around forever and is always there. And then you can use that to compute the limiting eigenvalues. So the one that was 0.2, just delete it. It's 0. The one that is 1, keep that at 1. Here's a little shortcut to do it. But it's doing exactly what I said. And then you can compute the matrix to the power infinity. So here is the matrix, the limiting matrix, 0.25, 0.75, 0.25, 0.75. That's saying no matter where you start, the answer will always be 0.25, 0.75. And look, it matches. It's really close to the matrix to the power 1,000, where you would be after 1,000 steps. So this is all the stuff we did before in pen and paper, now on the computer. That was a little bit quick, but it's all written here, and it's all stuff we've done. Any questions or comments about that one? Okay, so let's finally move on to where I've promised we would go for a long time, and we're finally going to do it today, I promise, is we are going to answer the question, how many visits are there to each square? So the number of times you visit. We're going to use this to answer how many rolls until you get to the end of snakes and ladders. And so last time I had this exact one on here. And we were trying to find an expression for the number of times you visit each square in terms of the probability vectors, the transition matrix, that kind of thing. And I think last time only like 5 people had an expression. We don't know if their expression was correct. Then I said go home and think about it if you want. So let me give you another minute. You can put in if you have an expression or not. How would you represent this random variable, the number of times a square is visited? Oh, and I want the expected number of that, right? So ns is a random number, how many times you visit square s. And the expected number total, so how many times you visit it in total, and time the expected value. And this made sense for snakes and ladders, because in snakes and ladders, you kind of visit each square a finite number of times, and then you end up at square 9, and then you stay there forever. So this is a finite number. Find its expected value. Okay, let me give you, say, 1 minute to do that. Maybe 2 minutes. And again, feel free to discuss with your neighbor if you want to check if your answer matches their answer. Okay, 10 seconds left. Put in your answer. If you don't have an expression, there is a button for you. So please, please click the I don't have button so I can know how many people. Okay. All right, let's take a look. Reveal counts. Okay, most people do not. Only 4 people found an expression. Let me give some hints to speed you guys along. So this is the kind of question you would do in a good probability class, or like a stats 101 class. So the number of times you visit state S. Number of times you visit S. So S is some state. In our snakes and ladders game, the squares were numbered 0 to 9. Of course, N9 is going to be infinity. How many times do you visit square 9 in a run of snakes and ladders? That's going to be infinity, because you eventually end up there and you just stay there forever. So you're like there for all eternity. N9 is kind of a boring one. N0 to 8 are the ones we're interested in. Another example I'll give you is N0 is always 1. Always. Because you start in square 0, you visit it 1 time, and then after that you can never get back to square 0. And the other ones, it's going to be a random number. Like how many times you visit square 2 is going to depend on how the dice come out. So it's a random number, but we want to figure out its expected value, which is a non-random number. Equals question mark. Okay, and I'm going to start with a nice way to write the number of times you visit something, which is the following thing. You can, how many times you visit something, you can count. Did you visit at time 1? At time, all right, I guess we'll start at 0. T equals 0. Did you visit at time 1? At t equals 1? At t equals 2? And you can do this forever. And you can add these up. So I'm going to put brackets around them. And I'm going to say, did you visit at each of these times? And add them up. So every time, the number of times you visit, I can break down as, did you visit at time 0? Did you visit at time 1? Did you visit at time 2? And if I add those up, if I have answers to these questions, each question I will think of as the answer as being a 1 or a 0. 1 if you did, and 0 if you didn't. In probability, we often call this thing an indicator function, and we draw a big 1. And if we're being very fancy, we put like a blackboard bold 1. That is the indicator function, which is 1 if the thing happened, and 0 if it didn't. We have an infinite sum of indicator functions. Who's seen indicator functions before in probability class? Who has not seen indicator functions before? Okay, good. So let's, now you know. So an indicator function, let me write down the definition then. The indicator function of some event, I'll write it like this. Did E happen? Normally people just write E, where E is some event. This is a random variable which is 1 if E happens, and 0 if E doesn't happen. Doesn't happen. And this is useful for all sorts of things in probability. You can write more complicated things in terms of these indicator random variables, which are kind of the simplest possible random variables, are either 1 or 0. Okay. Now ns is this infinite sum. Okay. If ns is an infinite sum, then the expected value of ns is also going to be an infinite sum. So let's write down the expected value. The expected value is going to be the expected value. Let's do expected value in a fun color. The funnest color I can think of today is black. Okay. The expected value of the indicator function of visit at t equals 0. Okay, and this is the nice thing about expected values, is expected values are linear. So I'm going to even skip a step. I should do the expected value of everything, right? You do the infinite sum, then you take the expected value. But expected values, you can do the sums in any order. So instead of doing adding them all up and then doing the expected value, I'm going to do the expected value of each one individually and add them up. That's always okay with expected values. Expected values are linear. They play nice. Okay, I guess it's always true if you have a finite sum. This is an infinite sum, so maybe something could go wrong. But you guys have to believe me that nothing will go wrong. And actually, you can prove it using the eigenvalue thing I said before. So in this case, it's totally fine. For finite sums, definitely okay. For infinite sums, sometimes you'll have some infinity problem. But this one is okay. Okay. So visit at time 2. Visit at t equals 1. Okay, and it's an infinite sum. It goes on forever. Okay, so you could write it with a big sigma, but I don't want to scare people from sigma. It's an infinite sum. Did you visit at time 0? Did you visit at time 1? Did you visit at time 2? The fact that n0 equals 1 is because this first term is 1 and all the other ones are 0. In general, all these expected values, these will be some numbers between 0 and 1, and you add them up. You do an infinite sum and do this. Okay, is this helping us answer the question? I took something we didn't know the answer to, which was this expected value, and I wrote it as an infinite sum of things that are potentially just as complicated. So the only way this is helpful is if these terms are nice. These terms should be nice. So what I want you to think about is, what is the expected value of the indicator function that you visited at some time? And you got to do the expected value of something that is either 1 or 0. Think about what is the expected value that is something either 1 or 0. These things, it turns out, are something we've seen before in the course. Okay, I'll give you a minute. Try to see if you can figure out what is this secret ingredient, the visit at time t, and then we'll go from there. Okay, so take, I don't know, 2 minutes to think. If you've never seen indicator functions before, this will be new for you. If you have seen them before, you'll remember. Okay, so let's reconvene. So the first kind of like thing you got to figure out to maybe simplify this is the expected value of an indicator function is something quite nice. So you have the indicator function of some event. I realized I called it E for event, but maybe E is confusing because E sometimes means expected value. Let's call it the event A. So if the event A happens, it's 1, and if it doesn't, it's 0. What is the expected value of the indicator of the event A? Does anyone know? Maybe I'll put it here so it doesn't go too far into the corner. Yeah.
The probability of A?
It's the probability of A. Yes, that's the probability of the event A. So, right? You get a 1 if A happens. That happens with probability A. 1 times the probability. If more accurately, you could say it's the 1 times the probability of A plus 0 times the probability of not A complement. That's the expected value formula. 1 times anything plus 0 is the anything. So that is the nice thing about indicator functions. Their expected values are probabilities. And so this whole infinite sum with expected values actually is going to be a sum of probabilities. And I'm going to delete. Can I make space using magic? Okay, I can. You know what I can do? I can select this. No, I can't. Okay. Maybe somebody else could, but not me. Okay. Let's take this thing and move it. All right. You know, I'm going to do the other thing what you can do, which is delete. Let's delete this one because I want the space to write down what this thing is equal to. This thing is equal to the expected value of the indicator is the probability. The probability that you visit at t equals 1, visit at t equals 2. Plus the probability that you visit at t equals 1. So you have an infinite sum of probabilities. The expected value of the number of visits is actually an infinite sum of the probabilities you visit at time 0, at time 1, and so on. And very fortunately for us, these probabilities are what we've been studying the whole time. We have a formula for the probability you visit at time 1. That was how we started the first problem of the first class, right? We had the snakes and ladder board, and I said, what's the probability you visit square 7 at time 3? That was exactly this kind of thing. And so you don't want to do the thing where you count up all the different possibilities. You want to do the thing where you write this as a matrix. So let's write it as a matrix. Let me make some more room here to write these things as matrices. Okay, so these things are matrices. If you start at time 0, let's call where you started, let's call that p sub 0. And so, for example, if you know you started at square 0, that would be the vector 1, 0, 0, 0, 0. That's 100% chance to start in square 0, 0% chance to start in all the other squares. That's p0. The probability you visit, visit where? Visit S at t0. Visit S. The S being what we're looking at. So what we want to do is going to do something involving p0 times the matrix to the power 0 plus p0 times the matrix to the power 1 plus p0 times the matrix to the power 2. And this is using the fact that the probability to visit state S at t equals 0, this is related to, okay, I'm not going to put equals yet, but it's related to p0 times m to the power t. I'm going to put t, a time t, a t. Okay, let me move this up a bit. So the probability you visit state S at t is related to p0 times m to the t. The thing that is missing here is that the left-hand side is a number. This is a number. It's between 0 and 1. It's a probability, right? You told me the state S. You told me t. I guess I could include starting at p0. Start at p0. But the right-hand side is a vector. This is a vector, right? The matrix M is the transition matrix of probabilities. I took it to the power t. I multiplied a matrix times a vector. That gives me another vector. So what is the relationship between the left-hand side and the right-hand side? If you write equals, it can't possibly be true. But they're essentially equal. What is the interpretation that you have to do? Or what do you have to do? Yeah?
There should be a row in your resultant vector that is like representative of that probability?
That's right. So this is a vector. And if you look at the vector, it has some number of numbers in it. And the numbers are exactly these things. when you go over the different values of s. So this number is one of the entries of this vector. So this is the number, and this is a vector. So you have two ways to sort of solve the problem. One way you could think of this thing as a vector by having s vary over all the things. So you could say the probability to visit, I'm going to call it state dot, this is like a thing people do, at time t, given you start at p0, that is now a vector. So instead of saying the state is state 1 or state 2, I'm like all of them at once. And if you interpret that, that is a vector of the numbers. That is literally equal to p0 times m to the t. It's the probability vector. We were calling this pt earlier in the course. So that's one way to solve it. Another way, so I kind of upgraded my number into a vector by thinking of the states as different locations. You can also downgrade your vector into a number by plucking out the right entry. How do you downgrade a vector into a number? You could say, take the s entry. So I could make this one an equality. Let me write it down over here. So the probability you visit state s at time t, given you start at the vector p0. You could say it's p0m to the power t, and then you could say take the sth entry, the sth entry, like so. Okay. So you can take the s entry. Sometimes people will just write an s. Another way you can take the s entry of a row vector is to multiply by a vector as well, a column vector, mt, and then you could do 0, 0, 0, 1, 0, 0, 0, 0. So there's exactly 1, 1, and that is in the s entry. Okay. So all sorts of ways to get the thing. I'm going to use this way to write it. So I'm going to take the p0mt and I'm going to multiply it by this vector, and you're going to see why I like this way of writing it in a second. But okay, before we go any further, any questions or comments about the notation? Yeah.
Would you be able to slide it all over?
Yes.
Slightly?
Yes. Like which way? Let's do it. You mean like this?
Yes.
Okay.
Thank you.
Yeah, absolutely. Yes, please let me know if it's hard to read. Okay. All right, so let's go back to our equation. Actually, let's just write our equation again so we can keep going. So the expected value of ns, and I wrote it as an infinite sum. Let's write it as an infinite sum now with a sigma. So you start at t equals 0, you go to t equals infinity, and it's the probability you are at location s at time t, and this is given whatever you started. Let's put that in as well. So given start at p0, given that you start at p0. Okay, and this thing we have an expression for now. The probability is actually something involving the matrix m to the power t. And instead of taking out the entry, what I'm going to do is I'm going to multiply by the vector 0, 0, 0 with a 1 all the way in state s. 1 in state s. And now I'm going to use the power of linear algebra again. If you have an infinite sum of a bunch of multiplications, instead of having an infinite sum of a bunch of multiplications, you could do the infinite sum first and then do the multiplications. So again, changing the order of adding and linear operations is okay. So let me do p0 times this sum t equals 0 to infinity m to the power t, and then times 0 dot 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 1, 0. The 1 in state s. Okay, so big infinite sum. This infinite sum, by the way, it appears, if you watch that Snakes and Ladders video, this is what they called I plus m squared plus m cubed plus m4. That's exactly where that came from. That's that infinite sum. So the expected value of the number of visits is an infinite sum. You could do this big infinite sum with the matrix, and then you multiply by p0, the probability vector on the left. You multiply by a 1 in state s on the right, and that gives you the answer. Questions or comments about this setup? Yeah.
Maybe a very stupid question, but
Yeah.
Is it important the order of the multiplication here? So p0 multiplied by the summation of the multiplications first before you multiply by the vector?
This is a great question. Say it one more time. So up here we're doing P0 times MT times this thing.
Yeah, I'm talking about like in your last line.
Yeah.
Is it important that you multiply the P0 by the like summation of the multiplications before you multiply in like the vector 0, 0, 0, 1, 0, 0?
Fantastic question, yes. Because there's three things, right? So there's this one, which is a vector. There's this one, which is a matrix. And there's this one, which is a vector. And you're saying, does the order matter? And as long as you do it from left to right correctly, the order doesn't matter. So this is a property of matrix multiplication called associative, I believe, which is that the A times B times C is the same as A times B times C. So it doesn't matter the order. Although, okay, it occurs to me, I did do something a little silly. Again, if you put this in a computer, it's going to explode and yell at you. So this whole thing is a correct thing. There is some technical reason this infinite sum is bad. But we'll get to that. It's fine as written. I guess the other thing I did is I wrote m to the power t. You have to know that I don't mean transpose. I mean really to the power t. So you really got to keep your head screwed on straight to follow along with all these things. But okay. Any other questions or comments? These are great. Okay. Follow-up question. We're very close. This is the number of times you visit some state S. Okay. What we actually want is the number of times you visit everything until you get to the end, right? How many rolls till you get to the end? And that is Mathmatize question for you. Take this, please modify it so it's what we want. Here we go. Number of total visits. Find an expression for the total number of terms the game will last, starting from the state 0, in terms of the math ingredients we've seen so far. So same kind of idea, but I want the total number of terms until you get to square 9. All right. And let me give you 1 minute. Or maybe a minute and a half, say, to do that. Okay, time's up. If you don't have an expression, please hit the button for don't have an expression so I can see how people are doing. There is a really easy connection between this thing, the total number of terms of the game, and the thing we just figured out, which is the number of visits to some state S. They're connected. Let's see what you guys said. Okay, 10 people don't have an expression, 6 people do have an expression. And let me give a hint, which is that the number of turns the game lasts is the sum of the number of times you visit all the squares 0 to 8. Right? So square 9 you will visit infinitely often, for sure, but squares 0 to 8 you visit each of them some number of times, and the total number of times you visit them is exactly the number of turns the game lasts. Okay, so the number of turns the game lasts is exactly number of turns is exactly n0 plus n1 plus ... plus n8. Okay. We don't include n9 because at n9 the game is just over, which means the expected number of turns is the expected value of n0 plus the expected value of n1 plus so on all the way up to n8. And we have the expression for these, right? So it's the sum. What was our expression? Our sum was P0, and then we had this sum, t equals 0 to infinity of m to the power t. That was the middle bit. And then we had the vector, which was 0, 0, 0, and then it had a 1 in position S. 1 in position S. And then we're adding this up, going from S from 0 to 8. Okay. So take what we had before, you add it up over all the positions. Yeah?
So this is the m with the like 1/6 factored out?
No, this is an m. M is an honest-to-goodness probability matrix. So m has the 1/6 in it.
Okay.
Which is actually, you can partially think of why does this sum converge. It's exactly because this thing will have these like 1/6 in it, even though it's an infinite sum, it'll sort of shrink down to 0. Yeah. Mm-hmm.
Did you just replace the last vector with a bunch of 1?
That's exactly what I was about to do. Very, very good observation. The stuff in the front here is the same no matter what the vector at the back is, right? So again, I guess we should sell a Power of Linear Algebra t-shirt because we're using it so often. Okay, so you have the sum of these things. 1 in position S. right? So this part is the same no matter what s is. The only thing that's different is this little vector at the back. And now we're adding them up. That's p0. The sum, there's a name for this vector. And the name of that vector is the vector 1, 1, 1, 1, 1, 1, 0, right? Okay, it's supposed to have like 9 of them. Okay, let's do it. Let's do it. I can count to 8. Let's do it. 1, 2, 3, 4, 5, 6, 7, 8. And then a 0. Okay, there we go. There's the vector. So 8 ones, and then a 0. Wait, hold on. There's 9 ones. Yes, thank you. Okay, good. So I can count to 8, but 8 is the number that we're not counting to. Okay, so there's 9 ones. The state's 0 to 8. All get a 1, and the last state gets a 0. That's the terminal state. We don't count that state. There you go. We have the answer. Very nice. Okay, questions or comments about this thing? So in the YouTube video, they just like say it. They're like, here it is, right? Now we've seen the gory details of where it came from. Let's do it on the computer and see what happens when we compute this matrix. Okay, so again, this is on the course GitHub if you want to follow along. Snakes and ladders. Let's reconnect and run everything. Run all. Okay, this is the stuff we were doing last time. We made the transition matrix. We computed the probabilities. We did that last time. Calculating the expected number of rolls to finish by infinite sum. So here is I plus m squared plus m to the n. Here's these indicator functions that we did before. Here's the indicator function st equals s that you're at the right position. And here is what my code does. It goes through, it does a loop over all times t, and it is adding up what you get. And so by adding up what you get, it's computing the first bit of this. So this is what my code does. My code calculates. My code calculates p0, and it's the sum from t equals 1 to, let's call it capital T of m to the power of lowercase t. So it's doing this infinite sum with a for loop by just looping and adding on one term every time. And here's what it looks like. So, okay, right now it's giving me a bunch of variables. This is a good pro tip. If at the beginning of your program you say set print options and you make the precision equal to 2, then it will only output 2 decimal places. Suppress equals true means please don't put anything in scientific notation. That also makes it easier to read. So let's try that and maybe it'll look a little nicer. Of course, sometimes you want more than 2 decimals, so don't always use it. But if you want it to look nice, okay, here we go. So here's what my computer outputted. Okay, gotta get to the right thing. So I start at some vector. I start at the vector, which is 100% of the time you're in state 0. Let's see. Can I finagle this to do what I want? Okay, so you start at the vector of 100% of the time you're in state 0, and then you're nowhere else. At time 1, or at time 0, that's where you are, the number of visits to each site. You visited site 0 one time. Then you roll the dice once. Where are you after you roll the dice once? You have a 0.17, that's approximately 1/6 chance to be in states 1, 2, 3, and states 5, 6, 7. That's what we saw last time. How many visits have you done to each of the squares? Well, you've done 1 visit to state 0 on average, and 0.17 visits to all these other ones. So it's just adding up these probabilities as you go. After 2 rolls, those are your probabilities, and here are your visits. Then more visits, more visits, more visits. As you go, these numbers get bigger and bigger. You'll see in particular the very last number. That's the number of visits to square number 9. And that one is going to get bigger and bigger because as soon as you finish the game, you just stay at 9 and you pick up a lot of value there. So here we go. 2.7 visits to 9, 3.7 visits to 9. You'll see that square 0 always has 1 visit. Square 1 always has 0.17 visits. That's because the only way to get to square 1 is if you rolled a 1 on the very first dice roll. Other than that, you can never get back to square 1. On the other hand, square 2, the probability is increasing, right? 0.49, 0.53, 0.54, 0.55. These are the number of visits to square 2. It's right around a half in the first 10, but it's slowly going up. Why is 2 slowly going up? Because if you land on the snake that takes you back to 2, you'll visit 2 again. So in principle, you can visit 2 many times if you get unlucky and keep hitting that snake. Okay, so these numbers go up. They go up, 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 right? By the way, there's a nice formula for the sum of all the numbers. The sum of all the numbers is just whatever turn number it is, because it has to sum every time you're adding on 1. You can see that already to 2 decimal places, there's a 100% chance you're done the game by now, right? The chance that you're still playing the game, that you're not at square 9, to 2 decimal places, the computer says is 0. Under the hood, it's still, of course, adding them up to many decimal places, but it's only rounding it to 2. And okay, things are going up. Essentially, the numbers aren't changing, and we're only adding 1 to the last one, because you should have done the game by now. But to be really sure, I did it. How many times did I do it? I did it 100 times. I added up the first 100 rolls. At the end of 100 rolls, I'm pretty sure you're done the game. If not, you're very unlucky. But should be done by then. And at the end, I got what? I got, scroll down to the bottom, I got this vector. So I did 100 rolls. That should sum up to 100. In the first 100 turns of the game, you're expected to visit the last square 96.63 times. You have like a 0.5 chance to visit square 2, a half a visit to square 2. So the total number of visits you had to square 2 on average is like 0.5. And that is the number of visits to everything. To find the total number of visits, we take this vector 1, 1, 1, 1, 1, 1, 1, 0. That's the vector. I called it reward. And I put in minus 1s. I'll explain why I put in minus 1s before. Let's make it 1s for now. And I'll explain the minus 1s in a second. Let's do 1s. So this is the vector 1, 1, 1, 1, 1 with a 0 at the end. And the expected number of rolls to the end is that vector times this guy. Right? So that, interpret that thing as a row vector, interpret this thing as a column vector, and multiply them together, the total number of visits at the reward vector 1, 1, 1, 1, 1, 0. And the total number of visits to end the game, we got 3.37. 3.37. And we were just replicating what we did in pen and paper here. This was the total number of visits, and this was what I called the reward vector. Reward vector. Okay. Any questions or comments about this one? One question you might have is, in the number file video, they said the answer was 10. So if you watch that video, they don't say 3.37, they say 10. Why do they say 10? Well, it turns out, if you watch the video carefully, they use the British version of the rules. And in the British version of the rules, if you go past square 9, you don't get to move. So we said if you go past square 9, you just finish the game. Like if you are greater than 9, you end the game. In the British versions, you have to stay. So if you put that in instead, very simple fix. We can switch to the British version of the rules and run it all again and see what you get. And in the video, they said 10. So are we going to get 10 as the total number? Let's go down to the place where we got it. Again, the vector looks a little different before. Look, you on average, you visit square, that's square 7, 3.5 times. So you get stuck at square 7 and you're like rolling. You got to roll in exactly a 2 to finish the game. So you visit square 7 a lot. Same reward vector as before. And you get the expected number of rolls to the end, 8.599. That's not 10. So what you have to do is go to the comments of the YouTube video and check and see other people who did it, who agree with you that it really is 8 point something, is not 10. So they lied in the video. This is a good thing to know. I think they were trying to say it's like approximately 10. So the real answer we're going to see is 8 point something. That's the real answer. 8.5999999. Of course, it's not going to be exactly 8.59999. There's one step in what I did here that is approximate. What is the thing that I did that's approximate? Yeah.
You only did 100 rolls?
That's right. I only checked up to 100 rolls. And in the non-British version, 100 rolls is you're pretty sure you're finished. In the British version of the game, I could see if you got really unlucky, right? It takes average like 10 rolls to finish. If you're super unlucky, maybe it takes you more than 100 rolls to finish. So let's check and see if it changes. If I increase this 100 to, I don't know, what should we do? 1,000? Computers are pretty fast these days. How long does that take? 1 second. Okay, great. Okay. And now it's 8.5999999. We have a whole bunch of 9s. So good evidence. We're kind of getting close to 8.6. We'll see if that's the answer in a second. But so far we have the answer. Okay. And we did it like this. The thing I wanted to tell you is that this sum, as written, will not converge on its own. And that is because the last entry goes to infinity, right? The ninth entry goes to infinity. Fortunately, the ninth entry going to infinity is perfectly canceled by the ninth entry being 0 here. So the combination of these two things is okay. You really should do it in the other order, even if you want to think about it like this. Question here, yeah.
Yeah, so if you did, I don't really know how you practically do this, but if you did extend this into infinity,
Yes.
would the expected value, it would be like 8.6, 8.6, 8.6, and then you get to infinity and it would just crunch and go
Yes.
to infinity? Is that?
This is a fantastic thing. And in the next 20 minutes, I'm going to show you how we can actually get to infinity. So far I've shown you in the computer that we can stop at some big number, and we should hope that's close enough. This is very similar to what we did for the probabilities. And let me remind you, what we did for the probabilities, we had P T. Let's talk about the limiting probability. The limiting probability. So the limiting probability is the limit as n goes to infinity, or let me call it t for time. T goes to infinity of p0 times m to the power t. Right? That's the limiting probability. Where are you at time t? Take the limit as t goes to infinity. So for the rainy day, sunny day, we saw that was converging to 25%, 75%. And you can really put that in the computer and get those lines. So for rainy day, sunny day, you can calculate with the computer, you can calculate these pictures, right? You can say, look, we're getting close to something. You can just take a really big number. You could go to time equals 1,000, and it's like you're pretty close to the limit, right? But we also found a way we could solve it exactly, right? So you can do this thing in two ways. You can, solution one, take t equals 1,000. And if you want to be really careful, you can check that 1,000 is big enough, right? You can check 1,000 and you check 2,000, and if 1,000 and 2,000 are almost the same, then you're pretty close to the limit, right? Just like a classic way of solving limits, plug in a huge number. That's solution one. But we also saw solution two, which was the eigenvalue way, and that involves solving p infinity times m equals p infinity. That was what we started today's class with, this equation. And of course, you have to be careful. You can't just put that in the computer. You have to make sure it's a probability vector. And you have to make sure that the limit actually converges to this. Like, if it's irreducible, then it works. So you have to be a little bit careful. But you can get the exact answer without doing a t equals 1,000 by solving some kind of linear system, right? And what I'm going to show you now is that you can do the same thing for this equation. So this equation, you want to solve it. It's got an infinite in it. You could take a big value, and you could say, I'm close enough. But you can do a trick and solve it exactly. And that's what I'm going to show you now. Before I show you, though, questions about anything so far? Okay, let's see the trick. And the trick was in the number file video. But again, they do everything super fast. And the trick was you replace the sum I plus m squared plus dot, dot, dot. They claim that this is the same as 1 over I minus m. And they have some like hand-wavy justification for this. I think the justification is the same as the fact that from calculus, 1 plus x cubed plus dot, dot, dot is equal to 1 over 1 minus x. This is the sum of the geometric series. And of course, in calculus, you learn it's not always true, not true for every x. You need conditions. It happens to be true in some sense for the matrix M. You have to be careful. In the number file video, you might have noticed they deleted a column and a row from the matrix. And they did that to make this thing actually work. So I'm not going to do any voodoo like that in this course. I'm going to show you a different way you can get the same kind of equation to come out. Question here, though.
Is the geometric series mean always true because this is a matrix of probabilities and it's all below?
Yeah, you're exactly thinking the right thing. So let me say why this is true. This is true when absolute value of x less than 1, right? If the absolute value of x as a number is less than 1, then this will actually be true as sums. This infinite sum will converge and it'll be equal to this number. This matrix equation, it's true when what? Well, m is not a number. I can't say what the absolute value is, but I can say the absolute value of the lambdas is strictly less than 1. So the eigenvalues. If the eigenvalues are less than 1, then this equation is literally true. Are the eigenvalues strictly less than 1 for the matrix we're looking at? Well, almost all of them are, except for there was one eigenvalue which is exactly equal to 1, which is that steady state eigenvalue. So for the matrix we're looking at, this is not literally true, but we did a thing. We put a 0 exactly in that last eigenvector of eigenvalue 1. So but this 0 sort of deletes the part of the series that doesn't converge, and then you're left with the part that does converge. That's what they did in the number file video. This is a little like weird to me. It's all true and it's all correct, but it's very slick. and it's hard to see what's going on. And the way we're going to do it, we're going to do something that actually relates to later in the course when we do reinforcement learning, is we're going to get this equation with the I minus m a different way using rewards. So rewards and value functions. That's how we're going to get the equation with the I minus m. Rewards and value functions. And in the first class, when I was telling you about what reinforcement learning is, I said it's these things like these Markov chains that are evolving, along with two other ingredients. One other ingredient is making choices. We're not going to use that today. But the other ingredient is rewards. So in chess, you get a reward of 1 if you win the game, a reward of -1 if you lose the game, and a reward of 0 if you tie the game. And in general, you can put any reward you want. So what is a reward? A reward, we're going to add it to our definition of a Markov chain. So we're going to look at a Markov chain with rewards. A Markov chain with rewards. So a Markov chain is just a sequence of states. Where are you at time 0? Where are you at time 1? And it's random, and it evolves in this specific way with the transition matrix. We have all of that like before. We're adding one new thing, which is the rewards. And the rewards are a sequence of real numbers. So that this is a sequence of real numbers. And you really should think of the whole thing together as being a sequence S0 R, let me make sure I get this right, because I'm going to screw it up. Okay. Make this one go away. Okay, R1, S1, R2, S2, R3, S3, dot, dot, dot. So the Markov chain is just a sequence of states. Where are you at time 0? Then you roll the dice, you go somewhere at state 1. Then you roll the dice, you're somewhere at state 2. And the rewards are the same sequence as before, but interspersed, you get some rewards, which are numbers. And the example I'm going to give you is if at state 0 to state 8 in the snakes and ladders, get a reward of -1. Why is it a reward of -1? Because in snakes and ladders, you're trying to get to the end as fast as possible. So every time you're not at the end, I hit you with a stick, right? I give you a reward of -1. And then you are trying to minimize or maximize your reward, which means you're trying to get to the end as fast as possible. So you get hit with a stick the minimum number of times. So if you get a reward of -1 every time you're at state 0 to state 8, and so let me write this down very precisely. RT, it's -1 if ST minus 1 is in 0 to 8, and it's 0 if ST minus 1 equals 9. So if you get to state 9, you just get nothing, and if you get in the state 0 to 8, you get a reward of -1. This is kind of like a parent who, when you bring home a test that is like a 95% test, and they say, but why did you lose 5 marks? That's the kind of rewards you're getting. You never get any positive rewards, no positive signals. The best you can do is get a reward of 0, and you will typically get lots of negative rewards while you're making your way there. So those are rewards, and you can use rewards to set up all kinds of things. Like I said, chess, any of those examples from the beginning of the course have rewards. And this is almost the setup. Once we add actions, that'll be the setup for reinforcement learning. So we're 2/3 of the way there. With that reward, there is something called the total return. And you should not mix up the return with the reward. I'll try to say the word total whenever I say it. The total return, it is the sum of all the rewards you will ever get. So GT is RT plus 1 plus RT plus 2 plus dot, dot, dot. Forever. This is an infinite sum. Okay. So this is called the total return, and it's the sum of all the rewards you will get in the future. With this setup, the expected value of GT, so in my example of the snakes and ladders, the expected value of G0, that is your total return at time 0, is exactly the expected total number of steps of the game. Or with a minus sign though, minus the expected value of the total number of rolls needed. So the total return if you make the rewards -1 for every time you're not at the end, the total return will be negative the number of steps you need. And again, you could equally well do it with 1 and 0, but then you don't interpret it as a reward. So a lot of people do this -1 thing. That's why we're doing it this way. Okay, so we've gone from calculating the total number of turns as an infinite sum to calculate the expected value of G0. But G0 is itself an infinite sum. So have we done anything? Like you could repeat everything we did, you get the same equation. But it turns out there is a really smart trick for finding the expected value of G0 as an equation. And what you do is you look at something called the value function. So the value function, and this is precisely what like chess programs do. So chess programs get a 1 at the end of the game if they win, and a -1 if they lose, and a 0 if they tie. How do they decide what move to make next? They use a value function. What is the value function? It depends on a state. So the value function will input some state S. So this is a state S. And it is the expected value of G0 started from S. S0 equals S. So you can think about it, the input is what state you're in, and the output is how much rewards will you get all the way up to the future, starting from where you are. Okay, that's the value function. And so, for example, in a game of chess, if you get a 1 if you're going to win the game eventually, and a -1 if you lose the game eventually, the value function will tell you which positions are good and which ones are bad. The positions that are good have a high value function. The positions that are bad have a low value function. So if you want to figure out what move to make next, just make the move that maximizes your value function. Make the best, get yourself to the place that has the highest chance of winning. In our particular thing, in our snakes and ladders, V of S is equal to the expected value of the number of turns given that you start at S. So you start at location S. How many turns will it take? Okay, with a minus sign. Okay. All right. And here is, so far we've done all this setup. We have these things, the rewards. We're writing things in a different way. The value function has a nice equation called the Bellman equation. I think Bellman was some British guy. And actually, I'm going to say what we're going to write down is we're going to call it the baby Bellman equation, because we're going to have a souped up version of this later, and the souped up version is what people call the Bellman equation. And the Bellman equation tells you what is the solution. It tells you an equation that V has to satisfy, and it says this. Let me just tell you exactly what it is. It says V as a vector. So again, V is a function, but it inputs S. So think about it as a vector. So think of as a vector over all states. And actually, it's going to be a column vector. Column vector over all states. So think of this V of S as a column vector, state 0, state 1, state 2, all the way up to state 9. It's a column vector. It satisfies this equation. V equals the expected value of the rewards in one step. So R1 given S0 equals S. So this is one step of rewards. One step. Plus V times M. Okay. Okay, and I'll prove this. This is actually not a hard proof. If you just take the definitions and you look at things, the proof comes right out. I'll do that next class. But this equation will give you a solution. And what this is saying is, remember, the probabilities were evolving according to the matrix M multiplied on the left. The value function evolves as the M multiplied on the right as a column vector. And you have this nice equation. This is very similar to, this should remind you of the equation, which was P equals P times M. This was the steady state equation. Remind you of this. So the probabilities evolve as row vectors multiplied on the left. The steady state equation is this. The Bellman equation is exactly like the steady state equation, but for value functions instead of for probabilities. And if you go to solve it, you will get exactly what we want. So in our example, what you get is the equation v equals 1, 1, 1, 1, 1. This is the thing with 9 ones, and then a 0 plus m times v. So v equals 9 ones and a 0 plus m times v. That's our snakes and ladders example, where you get a 1 every time you're in states 0 to 8. And this equation is exactly what they do in the number file video. Another way to write this is you could say I minus m times v equals 1, 1, 1, 1, 1, 1, 0. And another way to write that is v equals I minus m inverse times 1, 1, 1, 1, 1, 1, 1, 0. Right? So I promised you that I minus m inverse would appear. I think the right way to think about it is the Bellman equation, like that, with a v equals mv. The rewards are there. And if you have this equation, you can put it in the computer, and just like you solved the steady state equation, you can solve this equation. Just like before, the computer is going to give you a bunch of solutions that are wrong, that are not helpful. If you type in just this equation, then it won't give you the right thing always. You need to add in some extra things, like v of 9 should be 0. So if you add in v of state 9 equals 0, then we'll get the correct solution. And this is just like what we did as the warm-up problem today. The steady state equation on its own won't give you the answer, but the steady state equation plus some extra equations will. And you can put this in the computer as a big augmented matrix. I have that over here if you want to read it. Snakes and ladders. Okay, here we go. So solving the equation I minus m times v equals 1, 1, 1, 0, you get this answer. And you get the value 8.59999, which is, I think, to machine precision 8.6. Oh, look, over here, yeah. Here it found 8.6. Okay. So that's it for today. Make sure you check out the course link about the lab, which is on Thursday. There's like an FAQ there with things and a practice problem. And make sure you bring a laptop or something on Thursday. And you'll do some problems that are similar to these, and I will be here to help you. Okay, see you guys on Thursday.